Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very happy to introduce Eugene Charniak, Professor of Computer Science and Cognitive Science at Brown University. Eugene is known in recent years for being one of the major contributors to the statistical revolution in natural language processing. He's known for his work in statistical parsing, where his parser, with some help from people in the front row, is still the state of the art. And he really deserves credit for being one of the early pioneers in moving NLP to a statistical approach, having written a book titled Statistical Language Learning, published back in 1993 when there weren't too many other people doing this kind of work within NLP. Although our own Ken Church certainly was one of the other early pioneers.
Earlier than me.
In this area. If I can indulge a bit, I'd like to mention a couple of personal reminiscences of Eugene. I was thinking about what I was going to say when I introduced him, and I realized Eugene is actually the first person I ever met who was and is active in natural language processing, because it was several years before I got involved in the field. I was an undergrad at MIT, and Eugene was a grad student, and he was the graduate instructor in the Introduction to Theory of Computation course that I took in the fall of, well, maybe I won't say what year that was.
He got an A.
And so that course covered largely formal language theory and automata theory. There's been a lot more theory of computation discovered since then.
It was sufficiently long ago that people did not yet know about NP completeness.
Right. It was before Cook's theorem was proved. And if I can add another personal note, my younger son went to Brown and took his introduction to theory of computation from Eugene, covering the material, essentially the material covered in the course I took, plus a lot of stuff that's been discovered since. But that's the only course that either one of us has ever taken in formal language theory. So I think basically everything the Moore family knows about formal language theory can be credited to Eugene. In today's talk, Eugene is going to return to some concerns that some issues that he looked at in his doctoral dissertation, which I have a copy of here. I don't think Eugene will be offended if I say that probably the most important contribution of his doctoral dissertation was to demonstrate how really hard language understanding is, and in particular, how much general knowledge about the world you have to in order to understand language at a human level. The thing that most people remembered from the dissertation was an example that got much discussed. That was much discussed in NLP circles at least through the 70s. The example is Jack and Penny went to the store to get presents. Janet and Penny went to the store to get presents for Jack. Janet said, "I will get Jack a top." "Don't get Jack a top," said Penny. "He has a top. He will make you take it back." And so the point of this example was to say, what would you have to know in order to figure out that it refers to the top that was entertained as a purchase and not the top that Jack already has. But a few pages later, Eugene has a confession that shows how attitudes towards data have changed in the succeeding decades. With the exception of the example in 1.2, the examples used in the thesis are not real stories, but specially contrived examples to illustrate the point at hand. And in fact, the example that was most famous was not the one in 1.2, so it was one of the contrived examples. But all of us have learned a lot about how to deal with real data in the succeeding decades, and certainly Eugene has been one of the leaders in showing a lot of the rest of us the way. So without further ado, I'll let him get on with his talk.
Thank you. Yes, I remember Bob from that course, actually. I don't think I remember any other student. But okay, so I'm going to be talking today about generative models of discourse. And the work I'm going to be discussing is joint work with Mika Elsner, who is a PhD student at Brown, and Joseph Osterweil, who just graduated from Brown and is going to be a PhD student in Cog Sci working with, Tom Griffiths. Thank you. I mean, there was only one logical person at Berkeley if you're going into cognitive science. If you
Did I say Berkeley?
did I say Berkeley? Ah. Oh, okay, then there's only one logical person anywhere. If you're coming from Brown and did work with me and you're going into cognitive science, okay, it's either you go work with Mark or you go work with Tom Griffiths, right? I think that pretty much covers the possibilities. And I had hoped to have the work of a third undergraduate to discuss today, but his stuff hasn't worked. It's, quote, almost working, but I will not present it. So here's the abstract for my talk. Discourse, the study of how meaning of a document is built out of the meaning of its sentences, is the inter-sentential analog of semantics. In this talk, we consider the following abstract problem in discourse. Given a document, randomly permute the order of the sentences and then attempt to distinguish the original from the permuted version. We present a sequence of generative models that can handle the problem with increasing accuracy. Each model accounts for some aspect of the document and assigns a probability to the document's contents. In the standard generative way, the subsequent models simply multiply the individual probabilities to get their results. We also discuss the linkage of this abstract task to more realistic ones, such as essay grading, document summarization, and document generation. Well, I wasn't completely happy with this version, so I revised it. We present a sequence of generative models that can handle the problem with increasing accuracy. Each model accounts for some aspect of the document and assigns a probability to the document's contents. Given a document, randomly permute the order of its sentences and then attempt to distinguish the original from the permuted version. In the standard generative way, the model simply multiplies individual probabilities to get their results. In this talk, we consider the following abstract problem in discourse. I think by this point you've got the joke. Can you distinguish this document from the original? And of course, by your laughter, I think you all indicated that you could. Can we get a program to do the same? And if you think about it, this abstract problem makes a lot of sense, at least abstractly, because if you're able to do this, it's got to be on the basis of inter-sentential relations, because the individual sentences have not changed. So anything that enables you to distinguish here has to be something about discourse. And so this is a very nice problem. This too is made up. Okay, and so I've got the disclaimer here. In fact, however, if at the end you're interested, there is the original abstract that was that I assume you sent around. This is not identical to it. It's very close, but I made some changes to make so it would better illustrate the examples. And if you like, at the end I can talk about how my program does on the original with a real random ordering. This is neither. This was rewritten, and I changed the ordering to make the points clearer. Now, probably here I don't need to say this, but unfortunately in the area of discourse, there is not huge knowledge of machine learning. And so when I use the word generative here, I'm using it in the machine learning sense. And in particular, I do not mean a model that actually generates English or any other language. Rather, generative is used in machine learning to talk about a model that assigns probabilities to the input. So the word generate is can be roughly translated as assign a probability to. Okay? And generative models have very nice properties. And in particular, we're going to be talking about 3 models that assign probabilities to different aspects of the input. Okay? And as this says, one is the head nouns that occur, the other are pronouns, and the other is the actual syntax of the noun phrases. And the idea is that the probabilities assigned to the original document will hopefully be higher than those to some randomly permuted document. And thus we will be able to distinguish. And as the third point here, the advantage of generative models is that if done correctly, you simply multiply their probabilities together to get the final result. And in fact, that is exactly what we're going to be doing. We design each module independently, and at the end we just multiply the probabilities. So combining models is trivial if you've got a generative description. Coming up with the generative description generally is non-trivial. And so so there will be 0 time spent talking about combining models. All the time is going to be spent talking about how each individual model is constructed. So, more formally, we generate each sentence conditioned on the previous sentence. So here we've got some document D, and we're saying each sentence S sub I is conditioned on all the previous sentences. And then you multiply the probability of each sentence given the previous sentences all together, and you get the probability for your document. Now, for each sentence, we are going to compute 3 distinct probabilities: P sub n, P sub p, and P sub I. Okay, P sub n, P sub p, P sub s. P sub n is for repeated nouns. That's going to be one of our models. P sub p is for pronouns. So assign probabilities to pronouns, and P sub s is for noun phrase syntax. And so I'm going to be describing each model, and then as we get each model, we're going to do the multiplication, and I'm going to show how every time you do one of these things, the ability to distinguish random permuted document from the original goes up, needless to say, or else I would have inverted the sign and done the opposite. Okay, so our 3 models, as I said, are first for head nouns, which also, if you're familiar with this literature, the model goes under the name of entity grids. Second is pronominal reference. Third, noun phrase syntax. And finally, I'm going to talk about sort of less abstract problems that might actually be of interest to someone. So here's our original document. Discourse, the study of how meanings of a document is built out of the meaning of its sentences. It is the inter-sentential analog of semantics. In this course, we consider the following abstract problem in discourse. Okay, so the point here is that you've got lots of repeated words, okay? So discourse, discourse, sentences, sentences, problem, problem, document, 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 document. Models. Does models occur someplace? Yeah. Yes, models right there. So lots of repeated words. That was one of the things I did to make this point clearer. I added more repeated words. In normal speech, I wouldn't have repeated the word discourse here. I would have just said, in this talk, we consider the following abstract problem, and I just added in discourse to reinforce this point. So this particular portion of the talk is heavily indebted to work on what is called entity grids. So following Barzilai, Lapata, and Lee, an entity grid is an array with entries, really just the head nouns, of the document on one axis, the sentence ordering on the other axis, okay, and at each point in the grid, you note whether the entity appeared in that sentence, and if so, what role it played in that sentence. And we limit our consideration to 3 roles: subject, object, and other, or of course just not mentioned. So here is a partial entity grid for our document. As you see, discourse first appears in subject position, then it appears as other, and then never appears again. Document occurs every other time, initially, and then tails off. Problem here. So the point is that if you look at these things, the objects in question tend to be clustered. Hi, Ken. I didn't even see you there. Did you just walk in and I missed you, or?
Yeah.
No. Okay. So basically, the idea then is that in a real document, you're going to see this clustering effect. Okay, things tend to appear near each other and then tail off in either direction. Whereas in a random document, presumably that's not going to occur because you're randomizing the orders. So there's our random thing, and so before problem and sentences were close together, now they no longer are. And so if you just keep track of these things, you ought to be able to make the distinction. Okay, so here's basically what we're doing. As we noted, we're now considering the distribution P sub n, which is how the nouns of a sentence allows us, to assign some probability to S sub I given the previous sentence. In particular, we're going to restrict horizon, and I'm missing a parenthesis here by George. To the previous 2 sentences, making a Markov assumption. And so we're going to say, what's the probability of the noun of the sentence, of the noun in a role, n, given its roles in the 2 previous sentences, where they might be just blank. Okay? And so we're going to have these probabilities, and we're just multiplying all of them together to get the final number. By the way, this equation and almost every other equation I'm going to show you is bogus. Okay? It is a simplified version of what's really going on. I mean, there are real equations, but I just didn't want to. For example, to make this actually work, you don't want to consider just what roles it played in the 2 previous, but how many times you've seen it overall. So even if it hasn't appeared in the 2 previous, if it appeared 5 sentences ago, it's still more likely. Okay? But in that case, you don't keep track of the roles. So if it's 5 sentences back, you don't care what role it played, just that you have seen it before. So, yes?
So it seems like an alpha resolution would be really helpful here. Are you looking at pronouns now or no?
Hold on.
Oh, sorry.
You may remember there was a second probability distribution called P sub P. The lower one stood for pronouns. So
this is just the probability of
repeated.
something that's in a noun position being that particular noun. Or
It's if you're actually confused, I will answer the question, but to get into the real details would probably take me too long. But if you're actually confused, I will answer it.
I'd like to know.
Okay.
To be clear.
Okay. So
what this is estimating the probability of.
Okay. Here is the Let me just check what's on the next slide. Nope.
So,
So let me answer Bob's question, then I will get to you, Mark. What this is actually estimating the probability of is as follows. You have a sentence. You first guess what roles are going to be filled by entities that you've seen before. If it's a new entity, forget it. There's no way of guessing. Okay, so you first guess what the roles are. Now, given a role, guess which of the entities, by which I just simply mean head noun things, of the ones you've seen before is the one that's going to fit here. Okay, is that clear now? Mark?
Yes, I was going to say, don't you actually want to guess the role that the noun's going to play in the next sentence?
Yes, and I have elided that here. You may remember that I said you first guess the roles that are going to be filled by entities, and then given the role, you guess what the entity's going to be. So yes, I have skipped that probability. It's in the system. It makes a very small difference.
There's an obvious normalization question here.
Yes.
Are you going to get to that later? or
No,
anything?
that level of detail is way beyond anything I intend to get
These
to.
roles look sort of like Latin cases, like, you know, I don't know, nominative, dative,
Yes, yes.
ablative. I would have thought that something like given versus new would have been a better, a more useful sort of notion of role for this task than something like the Latin cases.
Of course, in English, subject is normally given. Everything else tends to be considered new. So
then you could simplify the system and just have two cases.
yes, you could. I am just following previous research here. I did not attempt to actually distinguish. Suppose we just had two cases, subject and everybody else. I simply don't know. I suppose you could find out. I wasn't greatly interested.
But actually, I mean, I'm sure the reason they did it originally was that if you want to predict the probability of a noun being repeated, it helps to know whether it was if it wasn't new, was it object or was it somewhere else? Because the probability of a pronominal anaphoric reference to something that wasn't either a subject or object is much lower than
That's probably, yeah,
of if it was an object.
undoubtedly.
You can construct examples that sound distinctly odd when you try
Right.
to use a pronoun to pick up something that wasn't either a subject or
Mhm.
object.
There was a question back there.
To double check that the subject and object.
Can you speak a bit louder?
Subject and object, they are the surface subject and object.
Yes,
not a
at the
deeper
moment
role.
they are surface. At least I think.
I think Bersley and Rapata's paper was using deeper roles.
Was it?
Yeah.
I don't
just
remember.
want-
This I did not actually write this program, so I don't know which way it is. I can actually run the program. How many advisors actually can run their students' code? So I consider that a major accomplishment. Okay, and it works. And it's actually very good C++. I was really impressed. Much better C++ than I write. Okay, so that's the basic idea. And here's the result. Baseline obviously is 50%. Okay, you have one, you have the other, flip a coin, get an answer 50% of the time. You're right. This model, entitled Model 1, gets 82.2, so we're clearly way above baseline. Not surprising. At least I don't think any of you should be surprised at this point either.
How much data do you need to train this probability? Assume you're doing the counting, right?
I'm sorry? How much is what?
How much you need to have the data to train this probability?
No, you don't. Well, you don't have to have any annotated data.
Just from whatever data you have.
You just take any document you want, feed it in. I mean, there's no training set here.
So everything except the occurrences is a given.
That's right, everything, yeah. I mean, so,
You have this row, right?
yeah,
So you
but that you get from a parser.
Oh, okay.
Yeah, so, okay, so we've got 500 million words of parsed data sitting around. Okay? We took, I don't know, maybe 5 million words and trained the system up, and then took another million words and used it as test data. But that, but aside from parsing it in the first place, I mean, that's the beauty of this task, right? You've got as much training data as you want.
For the test data, you just randomly permute the sentence.
That's right. You just take the sentences, randomly permute their order, and test. You could do it several times if you want, repeatedly test.
The task here is just, did A come before B or B before A?
No, which is the original, which is the permuted.
So then how it's based on 50%?
Because 50% of the time, you've got two documents. One of them's right, one of them's wrong. Yes?
Do you know what, if you actually selected the optimal ordering with respect to this model, do you know how often that is the true ordering of sentences?
Okay, let me just go on. I will answer that question in a second. So this is trained on, partially answers your question, 10,000 automatically parsed documents from the NTC corpus. It was tested on 1,323, okay? And the reason I mention this is because these documents are from the NTC corpus. They tend to be reasonably long, okay? Probably average length 20. We have done a test such as 20 sentences. So we have done tests for the test that Mark suggested, namely how often do you find the optimal ordering, on corpora which have shorter document lengths. Okay, and the trouble is that this isn't Markov anymore because you've got this long distance dependency on how many times the word has occurred. So you can't do any nice Markov type dynamic programming. Okay, so in fact what we did was we used simulated annealing. But by the time you get, that simulated annealing is fine if your average document length is sort of 9. But by the time you get to 20, it becomes, you've got a real search problem there. And that's another area of research that I simply didn't want to worry about. So for this corpus, no, we did not do that task. We have done a somewhat more interesting task. And I could have presented those results. That is, take one sentence out, and how often can you put it back in the right order? That's much simpler, obviously, since there are only 20 possibilities if you've got. And the results exactly mirror these results, except, of course, the numbers are much, much, much lower. Other questions? I'm happy to answer questions. That way I don't have to take them at the end. Okay? Okay, on to second model, pronominal reference. So the first question is, can pronouns actually help? They might help in two different ways. One is they might improve the discourse model the entity grid model that we just saw. In other words, if you knew about the other references, that might help you do the whole thing better. This is what the gentleman in the audience was suggesting. That is undoubtedly true. We have yet to get it to work. And we don't know why yet. I mean, so this research, by the way, this particular part of the talk I'm describing is very new. This is, we got this thing working in any form about 3 weeks ago. So needless to say, we don't understand all the things associated with it. But the answer to your question basically is yes, it ought to help, but no, we have not been able to get it to work yet. However, we can still ask this thing to generate the pronouns. Just like we said, remember this is all generate in quotes, generate the head nouns by saying that they must have been cued in by previous head nouns. You can say we're going to generate the pronouns based on the fact that certain head nouns occurred in the past, or certain pronouns. Okay? And the question is, will this help? And the answer might be no, okay, for several reasons. So first of all, if you take, I won't bother going to the abstract, but our abstract had very few pronouns. And the only important pronoun in the whole, there were only 2 important pronouns in the entire document, and they both were inter-sentential, which means that they won't help.
You said intra there.
The only important are in, that's right. What I meant is the only pronouns in the document were intra-sentential reference. And so thus they would not help us. Okay? Furthermore, when the document's out of order, there'll always be something for the pronouns to pick. Okay? So, why wouldn't it just be just as happy picking out some garbage referent? Okay? But as we will see, there is information here. Okay? This is the weakest of the methods in that if you only use it by itself, it doesn't do as well as the others, but it nevertheless helps in the overall mix. Okay? So, how do we do it? So to handle pronouns, we need to consider the various pronoun resolution properties, because as you basically have, what we want to do is we want to say, what's the probability that a particular pronoun has a particular antecedent? And then, given that antecedent, what is the probability that it will be the pronoun that you actually see? Remember, we're generating the words. Okay? And so in this case, we're generating the pronoun given the antecedent. And so what we, in principle, ought to do is sum over all possible antecedents and say, if you have this antecedent structure, what's the probability of that antecedent structure, times what's the probability of seeing the gender and, and whatever of the pronouns given the antecedent. That's what we ought to do. Unfortunately, that's computationally intractable, because if you have, say, 40 pronouns, there's 40 factorial possible combinations or something like that. Anyway, it's clearly, it goes up, very, very fast, and so we can't do it. So instead what we're just going to do is say, take the argmax, take the antecedent structure which is most likely according to our pronoun model, and then just evaluate that. And so, and this is reasonable, or it will become more and more reasonable, because as we add more and more information into our pronoun selection, there's going to be one right answer that's going to dominate everyone else, simply because we know that people almost never find actual ambiguity in pronoun reference. If you do, you say that it's a bad writer. So that's what we're going to do. And so now the question is, how do we generate our pronouns given that antecedent structure? We do it as follows. First, we say, what is the probability of the antecedent structure, of the antecedent, given the distance away from the pronoun that the antecedent is where it is found? And second, how many times the antecedent has been mentioned already? Obviously, the more times something has been mentioned, the more likely it is to be mentioned again, and the further away it is from the pronoun, the less likely it is.
Do mentions include an important mention?
Yes. Okay. So that's the probability that we're going to see A as the antecedent. Once we know that A is the antecedent, then we say, what's the probability that the pronoun will be of a particular gender, given that its antecedent is Alice, Bob, George, asbestos, whatever. And second is the pronoun of the right number, singular or plural. Okay, so that's the pronoun model. Here are some example pronouns. If the referent is X, and X is one back, i.e. the immediate neighborhood, and has appeared one time, the probability that it is the correct antecedent is one quarter. If it is one back and appeared more than 4 times, the probability goes up very, very fast to 0.86. Okay. The probability that asbestos is neuter is 0.998. And there's an interesting story about why it's 998 instead of 1. Basically, this was done. This is not there's nothing hand-tuned here. So this information was learned automatically. And I can go into how it was learned automatically if you're interested, but that's not new research. Probability that Alice is feminine is 0.84. By the way, the prior probability of something being feminine is 0.15, something like that. So, it did learn something here. Probability, here's an interesting one. The probability that it has a plural antecedent is 0.04. It's not 0. Okay? The problem that something, if it's her or he having a plural antecedent is, in fact, 0. My program...
So to do that, you need to do the partial first. Otherwise, how do you know that it here is not something like it is they will be something?
Actually, we get all those wrong currently.
Okay. So
Yeah, there are things called syntactic its that you're referring to, and currently we're just getting them all wrong. Heck with it.
Is that the reason why you get non-zero probability?
No, it's more complicated than that. But yeah, that's one of the reasons. I mean, but there's a whole slew of reasons. Okay, so those are some of the basic probabilities. Yes?
So will this model penalize a document that begins with a pronoun?
Yes and no. So what it does, it actually knows a little bit about syntactic its. So it says, if you're a document and you have it in subject position in the first sentence, don't penalize it too much. Okay? But if it's in any other position in the first sentence, then it's going to get penalized fairly heavily because almost all syntactic its are in subject position. So it knows that much. That's about all. And there was a question back there. Someone raised a hand? No. Okay? So those are some of the basic probabilities. So here are the results. By itself, it still does, a lot better than chance. There's not a heck of a lot of information there, but there's certainly enough. And it, sure enough, helps this. This is certainly statistically significant. I haven't actually done the tests, but, we're talking about 1,300 examples. A paired t-test, this is way significant. Furthermore, and here's an interesting thing, you can actually use this thing to test pronoun resolution. Okay, so here's the result we just saw. Okay, that's how well this document does, this model does, if you are using it to distinguish fake from real documents. If you use this thing with a weaker gender model, remember I said that gender was a big issue? So this model doesn't know enough as much. This is basically the starting model. We did a lot of self-training to get the model that this thing used. Okay, so if you took our starting model and used it, we'd still get, better than chance, but much worse performance. And then if you look down here, these numbers, by the way, should not be taken literally. Their absolute value should not be taken literally, but their relative values, the relative numbers are to be taken literally. Okay, so as you can see, the weaker gender model doesn't do nearly as well as the stronger gender model, and it very closely mirrors this. So I don't know if you'd ever want to do it, but if you wanted a task, if you didn't have training data for doing pronoun resolution, just use this task, and you've got all the training data, all the test data you want. Okay. Model 3, noun phrase syntax. If you look at the document, actually look at how each noun phrase is constructed. So consider the first use of the word discourse. Discourse, the study of how meaning of a document is built out of the meaning of its sentences, that's the full noun phrase. Consider the second use of the word discourse, just a bare noun. That is not coincidence. I rewrote this thing to make sure that... Right. Okay. The following abstract problem compared to the problem. That I think actually is not coincidence, but I don't actually think I wrote it into the example. I think this was just what I happened to write before I ever thought of using this thing as my example document. By the way, when I had the idea of using this thing as, you have some problem of figuring out how your talk's going to be put together. That was sort of the key. As soon as I had this idea of using the abstract as my example document, everything sort of fell into place.
Did you remember Becker's criterion?
No. What's Becker's criterion?
Every theory of, every paper about natural language processing should apply to itself.
There you go. Did everyone hear that? Every theory of natural language processing, every paper about a theory of natural language processing should apply to itself. Okay. Mark.
So I guess model almost works, right?
Let's see. Where are we here? So problem and problem.
Models, sequence of generative models. Or
right.
Generative
and
models.
Then each model.
Yeah,
yeah.
But look further down. Subsequent models.
Yeah. Well, as you know.
Out of 3.
Right. This is statistics, That's why statistics works and hard and fast rules don't, right? Okay. So the point I'm making here is that first mentions of objects typically have different syntax than subsequent mentions. They tend to be deeper in terms of their construction. That's the first point here. At every level of, so they tend to be embedded much more than subsequent mentions. They tend, at every level of embedding, they tend to be longer. Okay. And furthermore, there are certain key words. A is the obvious one. Tend to appear more often in the first mention than subsequent mentions. And other keywords also have similar behavior. So here was one thing I didn't know until about 10 years ago when I was doing a different study, that in most newspapers you almost never see the word Mr. or Ms. or whatever in the first mention of a person. It's always their full name, and never with a Mr. They never say Mr. John Doe. They just say John Doe, and then later on it will be Mr. Doe. Okay, so in this particular case, I'm giving it newspaper documents. It learns rules applying to newspaper documents. So there are these things that distinguish. Okay, and the point then is that if we assume that the first mention, that if we just track the head nouns of each entity and assume that each individual head noun refers to an individual entity, then the first time you see it, that's the first mention, and everyone later on is the subsequent mention. And for every document, you can say, what is the probability of seeing this version as the first mention, this one as the second, as non-first, non-first, non-first. And then when it's permuted, you will get a different order, and you will assign that a probability, and presumably there ought to be a distinction there. Okay. So, and again, we've got the following generative model. The first thing, so when we generate according to P sub s, that's the syntax, the first thing we generate is the depth. Let's see here. Yes, the first thing we generate here is the depth of the noun phrase. Okay, or the height. So h is the height. So that's how many layers of embedding this noun phrase has. Okay, and needless to say that first mentions are more likely to have high height. Everyone got that? And then, given its height, we're going to generate the rest of the syntax. And the rest of the syntax basically is for each s, where s is either a non-terminal or a key word, we say what's the probability of seeing it given the previous s, and the height. In particular, is this the very bottom level or not? And whether, and L, which is our label, is it first mention or not? So that's the generative model here for guessing the syntax based on, is this the first mention or not? Here's a simple example. So if we simply have the document, okay, there's the very simple tree for it. That's called height 1 because it's the smallest height you can have for a noun phrase. Okay, so that's P of H. And then what's the probability of the, given that it is the start of the noun phrase, there's nothing that comes before it. Remember I said that each conditional probability is conditioned on the thing that comes before it. Well, here the thing that comes before it is the pseudo symbol start. And that, and if it's the, if the label is not first, then this is going to be higher than if the label is first. Because the is more, A is slightly, more likely. I don't know if it's slightly more likely for first, absolutely, but certainly relatively to how it occurs for non-first, it's different. And so here is the result. That was our first model. That's when you added models 1 plus 2. This by itself does remarkably well. I don't quite understand why this thing, again, this is a somewhat new result. We did this earlier, but we didn't. I changed the training, training and testing set, and maybe I confused the two or something. But given that it's all unlabeled learning, it shouldn't make that much difference. But at any rate, this does very well by itself. But yet, all three still does much, much better.
And the combination method here is just multiplying.
Yes, and right. And there are no extra parameters. You just multiply the three numbers together, and that's it. You might, fool around with some weighting scheme, but we didn't bother. The idea was to keep this pure and to put all the effort into the modeling rather than the combination.
What
Yes.
kind of text are you doing here?
This is, as I said, all text from the North American News Corpus.
Right. So, I mean, something like a lot of these newspapers are written in an incredibly strong house style.
Yes.
First time.
And I'm picking that, and this is picking that up.
Right. You go for the appositive right after the
Absolutely. That's
keywords like spokesman or chairman or there are all these. Now, you don't have any way of measuring those, right?
no.
So you know
Other
about Mr. or something?
yeah, we know about Mr. We essentially the keywords are a, the,
Yeah.
and any word in first or last position that ends in a period.
I wonder if you could just train words that are found in lead sentences,
You probably could.
and that would probably be a huge feature.
Yes.
Um,
Yeah. Oh, there are zillions of things we can do. Okay. That's the beauty of this thing. It's finding new things to put in is no
I
problem.
wonder if you just picked a random sentence out of one of these things and asked humans, can they distinguish which sentence is the lead from which one isn't? Whether they would be, 2 or 3 nines.
I'm sure they would get it two out of 3 times. My guess is they would probably get it 4 out of 5.
Two nines.
Oh, no, not 2 nines. No. It's not nearly that good.
The lead sentence must be really obvious.
You'd be surprised. A lot of news articles, I've started looking at them. And a lot of news articles, you'd be hard-pressed to distinguish the lead from the, say, the first sentence of a paragraph, 5 paragraphs in, unless you knew what was recent information and what was old. So unless you follow the news and if you knew the date and could keep track of the dates of things, you might have a hard time.
There might be a significant difference with hard news stories versus
Oh, yes, there are. I'm getting a mix. I'm getting whatever was in the feed. But most of them are presumably hard news, and yes, there is a difference between hard news and feature. So, for example, in a feature, you can sometimes actually get first sentences that have pronouns, and they're just doing it for stylistic reasons. Yes.
So what do you think would happen if you use, say, Department of Energy abstracts instead of news stories?
Okay, so previous work, if you're familiar with the work I cited, was all on abstracts, and in particular, there was one about airplane crashes from the FAA, which is very similar to, okay? They are much shorter, they are stylistically even more constrained. This kind of stuff would be almost useless because everything is new. You never have positives, you never have everything's known to these people. Okay, the world is so small. So a lot of this stuff would be pointless. The entity grid stuff still helps. And there are other techniques that help in that case, but I don't want to go into, I'll get into that only in question and answer if you care about it. But some of these work, some don't. Pronouns, hardly any pronouns are so short. Let's skip that. Okay. So, I have these techniques. They work on this abstract task. And the question is there any real task? Okay. And before we get to it, let's just talk about how we could still further improve this abstract task. Next week, here's what I wanted. This is my goal for next week. Right now, it's saying if it's a pronoun, I'm going to generate it according to this pronoun model. If it's a noun, I'm going to generate this according to its repeated noun model. There's no probabilistic choice of should I represent this thing as a pronoun or a noun. Okay. That is presumably non-random, and presumably it depends on the order of the sentences in the document. And so just for tightness, if nothing else, I want to put that in. Next month, quotations. So first of all, there's the obvious thing that, I mean, this is cheating almost. If you permute the order, you may get a close quote before you get an open quote. Okay? I'm not proud. Okay? Use it. Less trivially, there are other phenomena that you only realize if you start reading the New York Times with the same eye that I do these days. It gets in the way of actually understanding the stories, but so for example, there is you almost never see a quotation in the first sentence of a news article. And when you do, it is what I would call a mini quote, i.e. 2 words quoted. So for example, you may remember the British sailors who were taken hostage by Iran, or as the Iranians would put it, were removed from their territorial waters by Iran. A news story came out about a week later saying that Tony Blair said that if the sailors were not released soon, Britain would have to pursue, quote, other means, unquote. That's what I call a mini quote, okay? Though that was actually the lead for one story. But a full quote, almost never. Okay? And that makes sense if you think about it. So there's a bit of information there. Furthermore, if you have someone quoted, and the next sentence, the probability the next sentence is going to be another quote is much larger than the probability abstractly. So it turns out there's a lot of information about quotation structure. Okay, and so I've got a student working on that, and that was the other undergrad who I had hoped was going to finish, and I could actually show that helped too, but hasn't been done yet. But he's very close. Okay, next year, temporal relations. Okay, what are things that are called discourse markers, like and, but, however, because. A lot of information there that people have been studying, but no one has done generative models of it, and no one has combined it with everybody else, and it seems to me someone ought to do that. Okay, more interestingly, right now we've got how nouns tend to repeat, but there's a lot of information on verbal progressions. Okay, how one verb tends to lead into another verb. There's a lot of information how one noun tends to lead into another noun. So if I say, if I'm talking about the airplane, I can talk about the propeller. But you would almost never see the propeller found by the airplane. Okay? So there's a lot of information there that we're not exploiting. Again, it would be interesting to start to access this. Real problems. Well, not real problems. Realer problems. Given an abstract representation of what we know about the entities in a document, really generate the words for those entities. Now I'm using generate in the literal sense. Okay? I mean, if you think about it, we're almost there. Okay? I mean, what we need is we haven't solved the search problem for this, but we've got a way of distinguishing a lot of the choices that go into this task. Okay? This has been done before. I think we can do it again and perhaps better. Whoops. Given the sentences of two documents, and the first sentence of one of them, pick out the rest of the sentences for that document. Okay? Shouldn't be that hard. I think we could probably do that right now. How about doing the same but with 10 documents on roughly the same topic? Now that's actually a very interesting task. Because if you can do that, you're getting very close to some problem in combining news sources into one document. Admittedly, only with the given sentences, but you're getting a lot closer. My point is that, yes, this task seems artificial, but there are, it seems to me, fairly clear ways of going from this very artificial task to ones that we might actually care about. And with that, I will take further questions.
Given the creative, do you also use the negative example or just the positive example?
Once more.
During the training, do you use both the positive and the negative example? Or
No, we only use positive examples. This is
do you use the negative example you have?
might be, but typically negative examples are associated with discriminative learning.
Yes.
And I wanted to avoid discriminative learning simply because I'm, as I phrase it, a generative bigot. I much prefer generative models just on aesthetic points. And second, because it allows me to simply create the models independently of one another and just multiply their probabilities together. And I just love that. I mean,
you don't need to go to the discriminative learning model. You can just train two models, one positive model. One
yeah, I understand, but I would have to do it for every time I add a new technique, I would have to redo the whole thing from scratch. Okay? And this way I don't. Every time I add a new technique, I just multiply its number in, and that's it. I mean, quite literally, that's what we do. I've never, I've never experimented with playing around with those numbers. I just multiply them in and the hell with it. I'd rather spend my time elsewhere. So no, I haven't done it, and I'm morally opposed to it. Yeah.
Eugene, could you say a little bit about how you do the training? Because, frankly, with so many hidden variables, particularly in the pronoun resolution model, it's notorious that DM often performs very badly without a lot of practice.
Yes. Okay. So first of all, as I said, there's one place where we actually used real live examples, real live training data, and that was in the pronoun stuff.
Annotated data?
Annotated data.
Okay.
So There I actually started with a small amount of annotated data, but most of the actual numbers were learned automatically because 99% of all the numbers are this information about gender. And there we used EM. Okay.
Did you use that annotated much data 10 years ago?
No, we used New G's data from about 10 years ago. Her PhD thesis at Brown was, she annotated some WSJ data.
Oh, okay.
Sections 0 and 1, I believe. So we happen to have that around. Yes?
I was wondering if you'd done this, probably not yet done the study, but if you just compared the probabilities of the first sentences of your two documents, how accurate would you be? Getting to the question of how...
probably more accurate than, yes, if you only looked at the first sentence of the permuted and the first sentence of the real, I think you'd probably do better, except, of course, 1 out of 20 times they'd be the same, and so you'd lose there. But assuming you removed all those cases, my guess is you'd probably do better because first sentences really are very different. They're longer. As the noun phrase constructions are different. They have much fewer in the way of pronouns, obviously, so yes, it would do better. Yeah.
Did you do paragraphs? Does your input have paragraphs? Do you try to paragraph?
The input, no, we have not tried to do paragraphs, but obviously that's a very interesting topic. Regina Barzilai has tried to do it, and I don't think with too much success, but I may be wrong. Yes?
For the current task, how high do you think the accuracy needs to be in order for you to start doing these other realer tasks that you mentioned? So now you're getting 70, 80, 90. How high do you want it to be until you're satisfied that you say, okay, we can move on?
I think long before I get to that point, I'm going to go to more realistic tasks. If I had to make a guess, so one question is, what's human level performance on this? And my guess is that human level performance is probably in the upper 90s, sort of. I don't even think it's like 2 nines or 3 nines. I think that, for one thing, as I said, my guess is human level performance is somewhere probably about 98. We have, once as a joke, Tom Griffiths said you ought to have a symbol for a number you make up out of whole cloth. And so now we have a symbol. It's 2 question marks, one on top of another. We call that the Griffiths uncertainty symbol. And so that number should have a Griffiths uncertainty symbol before it. Yeah?
So a related question then, I guess, is instead of just pushing this accuracy number as high as possible, have you looked at dialing how little permutation you actually do from the original?
No, haven't done that. But I think, again, actually, so one of the things we're now looking at is, this is Mika's doing this, and he's looking at chat rooms and trying to paste together the different threads of conversation using this. So that's another real a task you might actually care about. And so that's another related topic. So my guess is before, rather than doing that, I think we're going to, I, for example, would love to start working on this distinguishing documents from one another. I think that's, ultimately more interesting.
So when you multiply 3 probabilities together for the 3 models,
yes,
the assumption is that those 3 events are independent of each other.
That's right.
But in reality, you probably do conditioning.
You probably could. But they are pretty independent. One's measuring, if you think about it, there's no obvious overlap. Okay, there's probably some unobvious overlap. So one is measuring how nouns repeat. One is measuring how pronouns come about. And one is measuring the actual syntax of the noun phrase. Okay, so they really are, pretty close to, there's no obvious reason to think that they're connected. Undoubtedly they are, okay? Yes?
The first 2 may be connected cases, and that's how Bartley and Lee try to solve it, right? In the sense that, so not just by looking at noun phrases, they try to resolve the pronoun and pretend that there's a noun phrase in there, and try to use that like in the first model that you described. I don't think they made any improvements.
Oh, well, that's basically the suggestion that you made, right? That we ought to, or maybe it was, whatever, yeah. Yeah, we should do that, and we have done it, and it makes things worse so far. And we don't know why. But, you know, as I said, that stuff is less than a month old, so, you know, there probably is a reason, and it's just very unsatisfying that at the moment it doesn't help. Yeah, and by the way, when should I cut things off?
Well, the official end of the time is 3 o'clock.
Oh, okay. So, but feel free to leave, okay? Don't take me literally. Right. Yes.
Yeah, you mentioned that you like generative model in addition to personal preference. Is there any theoretical reason?
I'm sorry, say this again?
You mentioned that you like generative models.
Right.
Yeah. I mean, is there any theoretical reason or?
Sure. That you can just multiply the probabilities together.
Yeah, you can see this as a you can also see this as a weakness, right?
Why would you see that as a weakness?
Well, for a lot of information, probably cannot capture using using probability model and how.
Okay. So you're not saying that multiplying the probabilities is a weakness. That's obviously a strength because it allows you to not worry about that. What you're saying is you can't create independent submodels. And that is, of course, a worry. All I can say is that the 3 models I've got don't obviously interact in any major way, except for the one that we've already noted, and that I intend to eventually address. And second, there are about another zillion models I can think of that don't interact with these 3 or with each other. So all the stuff on quotations, okay, the stuff on temporal reasoning, all the temporal information that's in there, all the discourse information, none of that. You know, they're all predicting different words of the document and different things about the document. So I guess my point is that yes, there may be a time when I won't be able to see how to do it. And I'm always willing to bend my principles in the light of improving performance, okay? But in this particular case, I don't see the necessity of doing so. That's all I can say. I mean, you know, if you can think of some cases where I'd have to, what I will do is I will push those cases as far back as I can, and then I will try to think my way out of it, and if I can't, I'll bend to reality. Okay? But let me just finish. I actually believe that reality is that you don't have to do it. I actually believe that the human brain is doing generative modeling, okay? And, you know, when 150 years from now people discover it, remember who said it first.
Yeah. So obviously you took 3 models because you think they're probably the most important one to begin with.
No. No.
There's issue there.
Okay, because I thought they were important, and because I knew how to do them.
So the more you go, probably you pick up something less and less important.
Yes.
And then how do you weigh the importance about the model? When you multiply them all together, you don't distinguish how important one is over another.
That's right. And so
in many practical other systems, typically people don't weight models and then they train it weight.
Again, if you believe the generative story,
okay, you don't need to do that.
You should not need to do that.
Well, but on the other hand, maybe the counting, the training isn't accurate. And for that reason, you need to adjust how reliable.
Again, no. What should happen there is that as the models get worse, the probability distinction it assigns between the right one and the wrong one should grow smaller. Okay? And that should, in principle, do all the accounting you need to do.
That works as long as as the models get worse, it's just the variance that gets larger, but you're not accumulating bias.
Of course, of course. You don't think I would write biased models, do you? Well, not deliberately at any rate. Yes, look, I know all this. You're not telling me anything I don't know. But nevertheless, it seems to me a noble endeavor. Particularly, I mean, I'm dead serious about how I believe the human mind works, okay? I can't think of another story that is nearly as convincing.
Are you going to take your name off of all the papers co-authored between you and Mark, where Mark has taken your generative model and done some discriminative re-ranking?
As I said, I never let my principles stop me from improving performance. You heard me say that, remember?
And so the interesting thing is you actually have enough information here
to at least discriminatively combine the submodels.
That's right.
Right. That
You
would,
could.
That would be pretty easy
Yes.
to do. Yeah.
In fact,
Oh, sure, that would be very easy to do, obviously.
I was going to suggest that why don't you just get one of your students to code up a black box weight optimizer? Because where you see a generative model, I see a linear classifier with all features getting equal weight. It's completely equivalent. So if you're going to, if that's completely equivalent, why not just shove it, take your generative model, shove it into your black box weight optimizer and just optimize the weights, and whatever performance gain you get, and you don't have to think about it.
At the moment, this is true, but as soon as we can get the pronoun resolution system to actually produce information that the entity grid model can use, that will fail.
Okay. So the reason you don't want to do that is you're planning.
I'm hoping eventually that
variables that tie these.
That's right.
Together.
So yes, I could do that right now, except it would offend my sensibilities. But yes, and I probably could eke out some better performance. In fact, almost certainly. Okay?
That going that route also means you don't have to worry about all the submodels being independent.
That's right. But it would mean retraining every time that I add another model.
Yeah. But
Yeah.
For this kind, I mean, this is the kind of model you'd end up with would be a lot like the models people use in statistical NT, where you have a bunch of generative submodels. You have a few.
That's right, and they reweight them.
Just reweight them. And
Yes.
If you've got a small number of weights,
It's easy. Yeah.
up to 30 or 40, according to what we've heard rumors from Google.
Yeah.
You could just, you don't even have to
Absolutely.
do any fancy machine learning.
No.
You can do minimum error rate training.
Whatever. Yeah. Yes,
So
you're absolutely
It
right.
could just be a black box, and you don't have to sully your mind by thinking about what's happening inside it.
That's right. And maybe if one day I'm doing a task where I actually care about the output, I will do that. Okay? Because, I mean, if we actually care about, if we actually have something that people can use, and I can make it somewhat better by simply throwing it through a black box, I will do it. Yeah.
Have you found anything interesting about discourse in these models? What sort of hints are they picking up on to, quote unquote, learn about discourse structure?
Well, as I said, they're just picking up on the things that I've just been describing. Okay? Nothing more profound than that yet. I think I have hopes and fears about trying to learn discourse markers. Okay? My hopes are that it's going to pick up something perhaps more unexpected, interesting, than what we've picked up so far. My fears is that it's going to be as fuzzy as the field usually is. We shall see. That's why I put that one off. That entire area just, it's interesting, but often it can be awfully fuzzy. So look, I'm not going to claim that I have learned or produced or said anything interesting about discourse. Okay? Any more than I would claim that my parser said anything interesting about syntax. Okay? I'm interested in using statistical learning to attack language problems. And very often, what this means is you have to hit the surface phenomena first. And that's what I'm doing.
One other just clarification question. In training, do you train the models independently?
Yes. Yeah.
Actually, I like your belief to the generative story.
Uh-huh.
And I wonder, you can still use a generative model, but can you train it with some discriminative criteria, for example?
Of course.
So the model still generates the story.
It's called childhood.
Yeah, it's fun.
I'm dead serious. No one takes me seriously, but I'm serious. Is that it? Okay, well, thank you all.
Thank you.